Welcome back, chemistry fans. Today, what we're going to try and do is the second topic of Unit 4, dealing with the mole. This is the most essential topic that we can deal with the entire year. Please pay attention. Please take great notes. Practice often. Let's jump into what we need to share. All right, the mole. What is it? It is not a furry creature. It is a standard unit. It's just like a dozen, a decade, a century, a millennium. It's a value for some number that has been scientifically measured. So what it is, though, is used for atoms and molecules. Because they're so small, we can't just individually count those things. So we had to come up with some number to help us through that process. And the number that they've come up with is 6.02 times 10 to the 23rd. That is another name for what is called Avogadro'S number. And if I have this number of atoms, it will weigh different for different elements. So what we would have for carbon is that it would weigh 12 grams if I have that many atoms. But if I had copper, it would weigh 63.5 grams. And the reason is because copper has more parts. It has more protons and electrons and neutrons than does carbon. Carbon is element 12. Copper is element number 29. And so what we would have is this difference in mass, but the same number of atoms. And that term for those number of atoms is called Avogadro'S number. So we got to get used to the idea that a mole is this value. It's this 6.02, that is in reverse 6.02, 6.02 times 10 to the 23rd atoms. And that is a mole. So let's practice now what we already know about a mole value for how to convert between moles and grams. We already know how to calculate a molar mass because we did this last class. Molar mass is just the weight off the periodic table. So if carbon weighs 12, what we need to understand is that if I have 1 mole, that's 1 times 12 grams, which is 12 grams. So 1 mole of carbon would weigh 12 grams. Well, that would actually have 6.02 times 10 to the 23rd atoms. Well, what if I double the number of atoms? So I would have 12 times 10 to the 23rd atoms. Well, what would happen to the weight? Well, if the weight of 1 mole is 12, the weight of 2 moles, it would be double. So it'd be 24 grams. Well, let's go in reverse. What if I had 12 grams and I wanted to convert it into moles? Well, you could probably do this in your head. You're saying, well, 1 mole weighed 12 grams. So that means if I have 12 grams, I've got 1 mole. By the way, the abbreviation for mole is MOL. So if I have 25, wait, that's not the same. It's close to 2, but it's not exactly the same. So if I had 25 grams, I need to convert it by the weight of 1 mole. So I've got 25 divided by 12. So I can't do this one in my head. That'd be 2.1 moles. MOL is the abbreviation for the unit. Well, what if I start dealing with a molecule? So I do the same process, but I have to go and add up the weights. Carbon weighs 12, the oxygens weigh 16. If I add all that together, it's 44. So 470 divided by 44. And what you get is 10.7 moles. Now let's remember, if you're starting with a mole amount, you were actually multiplying by the weight. So let's go and add up their weights. 12 for the carbons, 4 for the hydrogens, that weighs 16. So it'd be 16 times 0.0396. And what you would get is a very paltry small 0.3 or 0.63. Now, what is the unit on this? We're converting it into grams. So in all these problems, we're either converting from grams or converting into moles. Well, what if, though, we can't actually weigh the stuff because it's a gas. It's floating up in the air. Well, what are we going to do to make a conversion? Well, there's a unique scenario that exists. At STP, for a gas, STP is the standard temperature and pressure. Now, what that means is the standard temperature is 0 degrees Celsius. The standard pressure is 1 atmosphere. So you're saying to yourself, well, 0 degrees Celsius, I understand that. That's freezing. 1 atmosphere, I don't understand what that means. That means it's right here in this room, if the room were freezing. Now, why would they choose that as the standard conditions to make all the measurements at? Because they want to get rid of the extra water that's in the atmosphere. If we freeze the temperature, all the water falls out and it's no longer a part of the gas. So we're trying to measure how much gas there is, but we don't want something mixed in with it that we can't see. So they freeze all the water out. So that's why they use STP. The unique scenario that I mentioned before is that it doesn't matter what gas it is. If I have 1 mole of a gas, it's going to take up the same amount of space. Any gas, no matter what it is, if I have 1 mole, it will take up 22.4 liters. Now, why was that value chosen? It was calculated. It was not chosen. I wish they would have chosen something that would have been easier to remember. It would have been nice had they chosen 100 liters, 10 liters, 1 liter, but they didn't. They calculated a value of 22.4, and we will get into this later in the year. We'll prove that this value is valid. But for right now, what we need to know is that 1 mole, it will take up 22.4 liters for any gas. Now, I'm not saying that the weight is going to be the same. The weight will be different for each one of the gases, but they will, in fact, have the same volume. So let's practice this. So we want to convert moles into liters. So when we do that, we will multiply by 22.4. So if I have 1 mole, I will have 22.4 liters. If I have 2 moles of the same stuff, well, it'd be twice as much. It'd be 44.8 liters. Let's go in reverse. What if I had 22.4 liters? Well, if I go in reverse, that means I want to divide. So that would mean I have 1 mole. Ooh, well, this one I can't do in my head, but I know the math is just divide by 22.4. And what I get is 2.5 liters. So I'm starting with liters again. Let's divide it by 22.4 and find out how much is 3.3 liters. It doesn't matter what the material is. I don't need the periodic table for these gas conversions because they're going to be converted into, because they're going to be converted into moles or liters, not anything to do with their gram weight. All right, and this last one, I'm given liters again, converting it into moles, 0.88 divided by 22.4, you get 0.39 liters, moles, sorry. All right, so now I've introduced 2 different ways in which we can convert. We can go moles to grams, we can go moles to liters. Next comes a little bit more confusing process, dimensional analysis. There are 2 ways in which we can sort this out, and you have to choose which is best for you. I'm going to suggest one, but this is the proper way to do it. We need to understand in dimensional analysis, like we did in the first unit, it means that you are converting from one unit to the next. And what you do is you always make sure that the unit you start with is canceled out by putting it underneath this process. So to go from 24 inches into feet, that means I need to divide 12 inches for every 1 foot. I multiply across the top, I divide by across the bottom stuff, multiply up here, divide up here. So 24 times 1 divided by 12 gives me the 2 that I want. If you need the actual steps in how to make these conversions, simply write out all the factors. That's the biggest key. Include your numbers with it and always arrange it so that the given amount has the cancellation unit, the same exact unit, diagonally from it. Then multiply across the top, divide by the values on the bottom. So if I wanted to convert 140 centimeters into feet, I would have to know these two conversions that are possible. We've dealt with these before. That for every 1 inch, they're 2.54 centimeters. Notice how the centimeters are both diagonal from one another. Notice how then the inches are diagonal from one another, canceling out, leaving me with the unit that I desire, which is feet. Multiply across the top, 140 times 1 times 1, divided by 12, divided by 2.54, and you get 4.6 is your answer. Now, doing another one of these for time or for a rate, speed, kilometers per hour. If I'm going 50 kilometers per hour, how do I convert this into miles per minute? Could be miles per hour, could be miles per second. They just chose miles per minute. So again, units for kilometers cancel out, top and bottom. Units for miles, units for miles did not cancel out. What I cancel out are the hours on bottom, hours on top. Ooh, that's a weird one. And what you're left with then are the units desired in this problem, which are miles per minute. After you multiply across the top, multiply across the bottom. Well, how do we use this then for our dimensional analysis of the mole? Well, let's say that you're given 11.2 grams of sodium, of salt, NaCl. We got to make sure that this gram is down below. We have to convert into moles, which is the standard unit, and then convert it into atoms. So what we're going to do is we're going to multiply the gram amount times the mole ratio times the number of atoms. Well, what this does is it cancels out the weight, and it leaves us with the atoms that we want. Or in this case, molecules. Now, this is a way in which you could try to understand the process, but I would choose to, in fact, do this differently, I think. I think what we can start to see is that there is a pattern that can be developed over here on the left instead of dealing with the conversions that are over here on the right. And this conversion process is going to be called the mole map. The mole map is a visual path to those conversions. I'm going to give you a moment here. I want you to copy this down, create your own mole map so that you can utilize it every time we have one of these problems, so that you can more easily see how to convert from moles to grams, moles to liters, moles to atoms. Without thinking about it, this mole map will guide you through the process. So let's jump into it. With the mole map, and I'm going to make this easier on ourselves. We're only going to go from grams. All right. So grams of potassium carbonate. Well, I need to give you that, K2CO3. You got grams, 590 divided by, because we're starting with grams and we're wanting to go out to formula units, which is molecules. So we're starting with grams. The only way to go through it is to multiply solid. I've got these backwards. Needs to be division here. It needs to be multiplication here. Needs to be division here. Needs to be multiplication here. Got that backwards. Boo. I'll fix that in the notes. So what I got going is we need to divide to turn it into moles, and then we multiply to turn it into atoms. So let's do that. Let's divide by the weight of potassium carbonate. I'm going to go on to the periodic table, and I'm going to get my weight. Potassium weighs 39.1. There's 2 of those. Carbon weighs 12.01. There's only 1 of those. And then there are 3 of the oxygens, 15.9994. So I'm going to go ahead and multiply 39.1 times 2 plus 12.01 plus 3 times 15.9994. And you get 138.2082. And we'll keep all of our numbers until the very last step. So don't use any sig figs until the last step. And then after we get this value, this will be our number of moles. So 590 divided by that value gives me 4.26892, blah, 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 lots of numbers. But that's not it. Now we've got to finish by multiplying by Avogadro's number. And we will get 2.57 times 10 to the 24th molecules. All right, let's do another one down below. So we've got atoms. This time we're going to go in reverse. The formula is manganese sulfate, SO4, 7. There's a lot of atoms in this one. So we got to go and look up. Manganese weighs 54.94. And that's multiplied by 2. There are 7 of the sulfurs, 32.06. There are 28 of the oxygens. Man, add all that together. 28 times 15.9994 plus 7 times 32.06 plus 2 times 54.94, and we get a huge value, 782.2832. Take that value later on. But right now, 8.3 times 10 to the 33, we will need to divide by Avogadro's number. So if we look at the mole map, we are starting on the far left, and we are wanting to go over to the far right. So what that means is we need to divide by Avogadro's number, and then we will multiply by that weight that we just calculated. So here we go. We're going to divide by Avogadro's number, and then we're going to multiply by what we just did here, the 782.2832. So all of this is going to come together. And I will get my final answer is 1.1 times 10 to the 13 grams. That's a lot. I don't think there's that much material on the whole earth. All right. Last, I've got liters going to molecules. So in this problem, I'm starting down on the bottom and I'm going liters to molecules. So I go up to moles and then I go out to atoms. So I've got to hurry up here because this is my last problem before I go and find people to help with bear block. So I've got 6.77 liters. I'm going to divide that by 22.4. And then I will multiply the value times Avogadro's number. So follow the mole map. So 6.77 times 6.02 exponent e to the 23rd divided by 22.4, and I get 1.8 times 10 to the 23rd molecules. And we are done. This is it. Thank you very much. I will talk with you again soon. Farewell.